There we go. Hello, and welcome to another rarely watched hangout with me, Danny, and Jimmy. This one is on quantum physics. So very simple subject here, not at all confusing. Danny, what do you know about quantum physics at the moment?
I don't even know what quantum physics is.
Excellent. Hopefully you won't get any tricky questions from you then.
You'll probably get this from me.
What's going on? Right, so quantum physics is the sort of big heading branch of physics. It's a branch of overall physics, obviously. And underneath it, there is quantum mechanics, and which is how matter interacts with each other bits of matter. So it's like classical mechanics, physics of things, and quantum field theories on the other side, which deals with things like how matter interacts with light. That's quantum electrodynamics. Or the physics inside of the nucleus of an atom, which is quantum, confusingly, quantum chromodynamics, simply because of quarks, different flavors of quarks and things.
What? A quark?
A quark, yeah. This is
what's a quark?
So protons in the middle of an atom. Okay, so on the outside of the atom you've got electrons.
Yeah.
And in the middle of an atom, you've got the nucleus, and the nucleus is made of protons and neutrons. Okay, yeah. And protons and neutrons are made of smaller particles called quarks.
Right.
Okay, and they are known as different colours, and that's where the chroma comes from in quantum chromodynamics, but we'll probably won't go there. Right. So you remember when we talked about relativity?
I do.
Yeah, and we said there was Newton over here. And
yes.
Newtonian mechanics couldn't explain certain things, and one of those things was the precession of Mercury around the sun.
Yes.
So Einstein said, This is like so totes simple that we don't even need to. I'll write it down, and created general relativity, which did explain what classical mechanics couldn't. But what he's obviously dealing with is huge, big objects in space, massive macro objects. Relativity is a classical theory, but updated. Classical mechanics somewhat. Quantum mechanics came from a similar type of thing, which is, science progresses because it's solving problems. Okay, and there were 5 sort of problems at the turn of the century. This is from the 19th century into the 20th century, and there were certain things where the understood model of the universe, or the understood model of atoms in particular, didn't seem to explain the experimental results from experiments that they made. So, prior to quantum mechanics, they did understand that things were made of atoms. They knew that much, and they knew that the atom was things were made of atoms. It knew it had atoms had a nucleus at the middle, at the center. Okay.
Yeah.
Rutherford fired some alpha particles, which are helium nuclei, at some gold, and he found that most just went straight through it.
Yeah.
But occasionally you'd get an alpha particle being reflected back off. Okay. So what he reasoned very cleverly from that was that most of the atom is empty space, but there is a hard nucleus in the middle. Okay. They also knew about the electron, And there were some different theories, like the planetary model, which was like the sun and the planets orbiting around the sun. What Rutherford thought with that planetary model was that the nucleus was in the middle and electrons orbited round. Now,
We use that in high school
there were
as
5.
a diagram.
Yeah, or in any science fiction program where they look through a microscope and see a nucleus with electrons whizzing round it and things like that. Okay. Now, under classical mechanics, okay, anything orbiting something either over time orbits down into the center, or it escapes. So it orbits faster and escapes. Okay, so over time, the classical model of the atom, what you'd find is that the electrons would all end up circling down into, because electrons are negatively charged, protons are positively charged, they attract each other. And so what should happen over time is the electron spins round, ends up in the nucleus, ejecting all of its energy as it goes, and all atoms would annihilate. So they didn't really understand, with their current ideas, how it was that atoms didn't just degenerate into little blobs and all matter fall apart. So they were quite, how is this the way it is? And naturally, you had the religious on one side saying, it's God's will.
Of course.
God keeps the electrons from going into the nucleus, and and naturally that was completely wrong and was just a synonym from we don't really know, but something's doing it. So that was a problem. That was a fairly large problem. The next one was spectroscopy. Okay, so at the turn of the century, the end half of the 19th century, there were a lot of scientists burning things and heating things up, and wondering what would happen if you looked at things. So the problems became more apparent when technology allowed you to make closer observations of stuff. Okay, so before Galileo, say, you would have looked up at the stars and the planets, and you would have just seen tiny points of light. And so you could have theorized that, and planet just means wanderer. So they thought, so they thought that the planets were wandering stars, so that they were the same as, they were same as all the other points of light, not the sun, but the same as all the other points of light, but just a few of them seemed to move about. That theory was modified when Galileo looked through his telescope and saw Jupiter and Saturn and Mars, and seeing they were not the same as these other points of light. So you had an extant theory that didn't explain the observation, and that's kind of what in there. And under spectroscopy, okay, going back to with the atoms, what they thought happened with atoms, okay, which was quite clever. When you heat something up, okay, the atoms vibrate.
Okay.
Okay, like what they tend to use is like springs. So if you fix the spring at both ends and wobble it about, the more energy you put in, the more it wobbles about. And then over time, the spring releases energy when you do that. So you put energy in to the atom then releases energy. So if you put in a little bit of energy into the atom, this jiggling, which you can do through heating, it emits this light, this radiation. And when they were heating all of these different chemicals and they were putting salt into flames, they saw that when you put salt into flame, for example, you got an orange light through a spectrometer. Yeah, it wasn't all light. It wasn't some white light, which is a mix of. It wasn't red, green, and yellow light. It was orange. Okay, and they heated other things, and they found that the flame colors, and when they looked through the spectrum, it was discrete lines of light. There were gaps between it. It wasn't continuous.
Right.
Okay, and as I say, the classical theory at the time made no prediction of this. So it said what should probably happen: the more you heat something, It should just give off more and more intensity of light. Okay. The next one was something called black body radiation.
Black what?
Black body radiation.
Okay.
Okay, and the ultraviolet catastrophe, which is very dramatic. Okay, and the idea, again, going back to classical mechanics, and this idea of the atom is this jiggling thing. They didn't really understand what was going on inside the atom, just that it jiggled when you heated it. And the reason they thought that, if you heat metal, it expands. And what they thought was happening was the jiggling was so much that the length of a metal bar when you heat it grows because everything's vibrating more inside. You weren't getting more mass; it didn't weigh anymore. It just expanded. Okay. Now, a black body is an idealized bit of stuff, and it absorbs all radiation that's incident on it. So when you shine a light on something black, it absorbs loads of light. Yeah, but you can still see the object, so it does reflect some of it. But a black body, an ideal black body, absorbs all the light. Okay, but it also radiates all the energy. Okay, because if it didn't radiate the energy, you break the second law of thermodynamics, and you could put a black body into a room, and the room would tend towards absolute zero, and the black box would just get hotter and hotter and hotter and hotter and hotter. So obviously it's absorbing all the energy, and then it's radiating all the energy. And when you heat something up, it starts off the color it ordinarily is, and then it gets red, yeah, and then it goes yellowish, and then it goes white, yeah. So as you heat it up, it gets white hot. And what they thought was, well, if what's happening is you get this jiggling, when you add more and more and more and more energy in, there should be no upper limit to this jiggling. So you get something hot enough, it goes white hot, but then it should produce lots of ultraviolet radiation, it should produce X-rays, and it should produce cosmic rays, but they didn't know about cosmic rays. But the point is, the more energy you put in, the higher the frequency of the energy out. So, and what they thought was it was intensity that was causing this, that should cause this. So the more energy you put in, it goes from, it gets hotter and hotter and hotter. Yeah, put simplistically. And then there was also the photoelectric effect. Okay, and what they noticed there was if you put some metal out in the sun, and this happens on oil platforms and things. Everything has to be very well earthed, because the sun on metal, it starts to build up a charge. It starts to build up static electricity. So you have to earth yourself, otherwise you can have these sparks, and sparks aren't great on an oil platform. Yeah.
Makes sense. Yeah.
Yeah, things okay. But of course, the understanding of light was that it was a wave. And you had this example of, it builds up this charge, but they were thinking, well, why does it build up the charge? Well, it must be removing electrons. So light's coming in, and it should remove electrons. And they did some experiments, and what they found was when they shined red light on the metal, no matter how much they increased the intensity of the red light, so the brightness of the red light, no electrons were ejected. But when they shined a different color of light on, like violet light on it, you would start to get electrons. But the energy of those electrons coming off didn't depend on intensity. So no matter how bright you shone the light on it, the electrons coming off didn't go any faster. They only came off at the same speed. It was just more of them with the intensity. Okay? And the last sort of problem was something called heat capacities. I don't know if you know anything about it, but it's the amount of energy that you need in order to increase the temperature by 1 Kelvin, which is the same as 1 degree Celsius. Yeah. So when something's really, really hot, you add a certain amount of energy to it, and it increases by 1 degree centigrade, 1 Kelvin. Yeah. And when something's very cold, you add some energy in, and it increases by a degree Celsius. So the classical idea was that this was, temperature wasn't related to it. So something that was very, very cold, you added X amount of energy in, it would increase by 1 degree. And when something's very hot, when you add the same energy in again, it should also increase by 1 degree. But experimentally, that wasn't what was happening. Yeah, so they did these experiments, and those experiments all contradicted all of those different things. Okay, so at the turn of the 20th century, people started thinking about this, and one person that started thinking about it was Max Planck. And Max Planck was employed by a light bulb company. Okay, and the light bulb company said, well, how can we make our light bulbs super efficient? Because this is a bit of wire that heats up and produces lots of light, and what we don't want is waste energy. So most of the energy, the electricity that you put into a light bulb goes into heat, and only a tiny fraction of it goes into light. And they recognized this was incredibly inefficient. So they asked Max Planck, how do we make more efficient light bulbs? And so he investigated this black body radiation and wondered why there was this, you didn't see this ultraviolet light, just, you don't get ultraviolet light coming out of it. So you don't have this objects starting to emit ultraviolet light, which is handy because we would die if it did. So he said, right, well, what's happening with the black body radiation, okay, is there's something about it, okay, that doesn't allow energies above a certain level. Okay, so it doesn't just keep going up and up and up. So the more energy you put in, it starts producing X-rays and cosmic rays. It doesn't, So he started off by looking at the experimental results and then reverse engineering his equation into it. And what he found was there was only certain wavelengths of light that were allowed, and those certain energies of the light, and those energies were discrete, so they weren't continuous. And the energy of a particular color of light was very specific and was related to something called the Boltzmann constant, which you probably don't know. So I'm trying to do this without any kind of maths in it, but the average energy going in of any object, okay, is equal to something called the Boltzmann constant, and its overall temperature in kelvins. Okay, and the wavelengths were all at the were never any greater than the average energy. So he did some measurements, okay, and he found out that they were all the energies that came out, none were greater than the average energy going into the box. So if you imagine a bell curve, yeah, and the peak of that bell curve is the average energy, yeah, and then it curves down like that, so that there's a very few number that have ridiculously high energies, and a very low number, and also an equally very low number that have no energy. Yeah, and what he realized was that there was the link between this average energy value and the energy coming out of it. So the vast majority of light coming off of it only ever could be just below UV light, but you'd get a few. But the point was the probability of getting any photons that were higher energy was exceptionally low. Okay, and from this, and the fact he was a genius, he worked out that energy is quantized.
Is what?
Is quantized. Okay, so you can't have any value of energy. Yeah, he figured that all energy was quantized. Okay, now there is a slight clarification here in that, and that's where you get quantum mechanics, the idea of quantum mechanics for. So prior to this, okay, they thought it was continuous. Yeah. So that because all it depended on was this jiggling of an atom. Yeah.
Right.
And an atom, and why should it be that you can have this frequency of jiggling, yeah, but not this slightly higher frequency of jiggling? What would happen is you get this jiggling, or you get this jiggling, or you get really fast jiggling. Okay.
Yeah.
Yeah. So he said, right, well, it goes in steps. It's not a slope. It's a flight of stairs, if you like.
Mm-hmm.
Yeah. So it's either this or it's that. It's never that. Okay, and that's what he observed. Now, then Einstein was working with him on all of this, and he did the photoelectric effect experiment, which was the other thing where you shine a light on something and it builds up a charge.
Okay.
Yeah, and he realized that it was dependent on the frequency of the light, not its intensity, that explained how fast the electrons were coming off of it and building that charge up. Okay, so the point to take away from this is that he was firing photons of light and changing the frequency, and it was the change of the frequency that caused the electrons to shoot off at faster and faster speeds. Okay, so both of them created formulations, so mathematical formulae that explained the results. So for things you put in, the energy you put in, here are the things that the outputs vary by. And Max Planck kind of took the view of, well, I've explained it mathematically. I don't need to sort of tell you what's going on inside there. The maths predicts what actually happens in reality. And Einstein thought, well, that's not ideal. We should be able to explain what's going on as well as mathematically model it. So you had this, and Einstein was very, very clever, and he's involved in most of these different things. So heat capacities, he did the thinking of, and what they had to come up with was something that was totally different to what was seen before. So under classical mechanics, energy was contiguous. You know, it could be any value, but now it was quantized. It was coming in discrete lumps. Okay, which suggests that light is not a wave. Yeah, if light's coming in discrete lumps, yeah, so light, the color of light explained the energy in that light, in that lump. So when Einstein was firing these lumps of light at a piece of metal, it was knocking off electrons, and those electrons had a fixed energy which you could measure, and that fixed energy that you could, the kinetic energy of the electron was related to the frequency of the light. So if you increase the frequency of the light, so if you change the color of the light, you shorten the wavelength, more energy, and so they came up with this idea that E equals HF. Okay, so you've heard of E equals M squared, E equals MC squared. We've now got E equals HF, and H is a fantastically small number. Okay, it's known as the Planck's constant, and you see it throughout quantum mechanics. Okay, and it's used as this thing that gives stuff steps. So it is a bit of a reverse engineering of the observed results into a mathematical formula that allows you to predict what's going on. But at the time there wasn't an explanation or interpretation of those results. Okay, to say, right, this is what's actually happening with the electron, or this is what's actually happening with. So you think of a body falling to Earth. Yeah. It falls down, and you see it fall down, and you can picture it, your mind falling down. And nobody could really understand what was kind of going on. And so Niels Bohr came along and said, this is really super duper interesting stuff. And he came up with the idea, because what you didn't have, quantum mechanics only seemed to relate, you only saw these behaviors at the small scale or low energy or low temperature things happening. The classical mechanics still held for everyday experience. Okay? And so it was quite a small field of study, but it was the frontier. So the really brilliant minds came in and started looking at it. And they found out certain things. One of it, you'll hear people will say that all energy is quantized, as I said earlier. It's only bound energy that's quantized. Okay, now bound energy, bound particles are particles in which it can't get out. So this is far more complicated than I thought it was going to be. If you imagine something falling to the earth, okay, again, and it's a ball, it's a bouncing ball, and it falls down, and when it bounces up, it doesn't fly off into space. Yeah? Because the energy of the ball is lower than the potential energy of the Earth's gravitational field, yeah? So you have to throw the ball with, you have to make the ball go at escape velocity. So its potential energy is greater than the potential energy of the Earth. And only when that happens can you actually get out and leave Earth's gravitational influence, yeah? So the ball is bound to the Earth. Okay, same example for an electron. The electron is bound to the nucleus because they have opposing charges, and opposite charges attract. Yeah, okay. But if you give that, sorry.
So okay, yeah.
Yeah. So what's happening is the photon of light, the lump of light, they called it a photon, Greek for light, and it comes in. And it gives that electron a certain amount of energy. And when it's over a certain amount of energy, so when it's a color of light like blue, that's enough energy so that the electron can leave the atom and is ejected off into space and is detected, and you can measure its kinetic energy. But light of a lower energy doesn't eject that electron. Yeah? So the electron is bound to that proton, and it forms an atom because of it. So what they noticed was there was this threshold energy. It was quantized. There was a link between the energy of the photon and the speed of the electron. So the electrons around the atom were quantized. Yeah, they only had specific energy levels. They couldn't just be anywhere. Yeah, they had to be either here or there. Couldn't be there. Yeah, and that's as much as they knew. And so there were two people that, the next two stars, if you like. Actually, there was another experiment. I'll talk about this other experiment just quickly, which was Thomas Young's experiment, which is the double slit experiment.
Right.
I don't know if you've heard about this, but what he found was, well, if I shine a light through two slits, I get this lovely interference pattern that you get if you imagine a harbour and you get waves coming out of the harbour. If there's one hole in the harbour, it goes in a nice crescent thing. But if you get two holes, then the two interfere with each other and you get peaks combining with troughs. And if you've got a speaker system at home,
yeah,
okay, if you've got two speakers next to each other like that, and you walk around your room, what you'll notice is there's loud spots and quiet spots.
Yeah.
In the room, because the waves coming out of the speakers are in sync.
Right.
And sometimes they interfere with each other and cancel each other out. So if you imagine a wave looks like that, when you have a wave that's a trough and a peak, two waves like that, they cancel out. So if you look at some pictures of the sea, like going through a boat, you'll see that it's not all peaks. There are high bits and low bits and all this. That's because there's all these different sources of waves, and some of them cancel out. Okay, this is something they noticed. They noticed this happened. Okay, now you've got this wave thing, and that seemed to contradict Einstein's view that light was particles. Yeah, it was these lumps of photons. And what they figured out, what they saw was when you fire, imagine you're firing, I'll use Feynman's example, imagine you're firing bullets out of a gun, okay, and you fire it through one slit, okay. Some of the bullets hit the side of the slit and fly off all over the place. Some of them go straight through. And what you'll notice on the target behind is they're all localized within a lump, yeah? Or, you know, there's no holes over here, it's just behind the slit. Yeah? Because the bullets fly in straight lines, and the ones that go through go straight through. Yeah? Now, when you have two slits, you get two lumps, two sets of holes, yeah?
Right.
Behind the thing. So what they said was, well, if light is particles, when we open one slit, we'll see a load of light behind that one slit, yeah?
Right.
Because they're like bullets, they're like lumps. And when we open two slits, we'll see two lots of light bars behind the slits, okay? Because they're like bullets. We said they were like bullets, okay? And what they found was that when you had two slits, you got the same interference pattern as you do with the cold and loud spots in your room with your sound system. So from that, they said, right, well, light's a wave then. Yeah? It's not these lumps, it's a wave. And so they said, well, okay, but we've got this evidence over here that shows that it's lumps. It's not a wave, it's lumps. Yeah? And so they had these two irreconcilable ideas. So a guy called de Broglie said, well, if waves can sometimes act like a particle, can particles sometimes act like a wave? Yeah? So he said, this is super cool. And so they tried it with electrons, which they realized were lumps, because when you throw an electron at a wall, the wall increases by -1, if you like, the charge on an electron. Yeah, so nowhere did it hit and say, well, this is half an electron's charge. No, it came in lumps, and it was always electrons. But what they found when they fired it through a diffraction grating, these two slits, you got the same interference pattern. So you say, yeah, sometimes matter acts like waves, and sometimes waves act like matter. So there was this wave-particle, what he called wave-particle duality. Okay. So I know this is so complicated, isn't it? But the point is this is remarkable.
Is it?
Yeah, that sometimes waves act like particles and sometimes particles act like waves.
Remarkable.
Yeah, because you think of a bullet being fired from a gun. You know at all the points you can see where it is, and if you take fast enough pictures, you can see the bullet moving through space, and at all times it's acting like a particle. Yeah. But what they found was that depending on how you, when you fire the light through the two slits, or when you fire electrons through the two slits,
yeah.
Why is it not like bullets? So, like I say, when you have the two slits, you get two lines of marks on the target. Yeah. So, but what they found this interference pattern. So they said, right, well, if you've had these two lines with bullets, you can work out, does it go through that slit or that slit? Yeah. And so they shone the light. They closed one slit, yeah, you only got one bar. They closed the other slit, yeah, you only got one bar. You open both slits, you get this interference pattern. So they thought, well, how can we find out which slit it's going through. And so they came up with an ingenious idea of how to figure out which slit, if we do it with electrons, the electron was going through. And they used light to do this. And if you shine light of a certain frequency on an electron, when the electron hits the photon, it releases light off. So when they could tell which hole the electron went through, yeah, then you got the two lines, like as if you were firing bullets. So they came to the realization that when you know which hole it goes through, it acts like a particle. When you don't know which hole it goes through, it acts like a wave. Yeah, so it depends on, you know, whether you know which hole it's going through. So when you're looking at it, it acts like a particle, and when you're not looking, it acts like a wave. Yeah. So, which the reaction, I mean, most people would say this is not the way that matter and things in the universe act, is it? You know, so it seems quite weird. But all of the experimental data went with that. You know, that was how it is. And so there were these two chaps, Heisenberg and Schrödinger. Have you heard of these people? No. Right. So Heisenberg.
I'll tell you something, Dan. Right. The only reason that I used to go to science at school is because I used to sit next to a girl that had wandering hands.
Did she?
Yeah.
And when the teacher wasn't looking, the hands would wander.
I got busted once actually because the teacher caught us in an interesting, compromising position.
Were you in a tryst?
Yeah. Yeah. Anyway,
well,
so yeah, science for me was just that.
Something other people did.
Something which you know about, however, I didn't think about.
Yeah. So, and as I say, science is, the reason all of this was done was because they couldn't explain the experimental results. So they said something else must be going on here. And there was a famous Nazi called Heisenberg, Werner Heisenberg, and wasn't a Nazi, Erwin Schrödinger. Okay, and both of them came up with different formulations of what was going on. Okay, to try and explain, well, what happens to an electron, say, when you fire it through these two slits? And what they realized was that it was entirely random what happened. So it would always form the same pattern, but for any individual electron, you couldn't tell where it was going to go. So it could either be in place A, B, C, D, or E, let's say. And for any individual electron, it was entirely random where it came out. Now, prior to this, the view was that the universe was entirely deterministic. Yeah, so that if you knew the starting conditions of the electron, you could work out exactly where it should go. And what they found was that at the smallest level, this didn't happen. And Einstein said famously, "Oh, God doesn't play dice." So he didn't believe that things, you know, he thought there was some hidden variable that meant that you could work out, if only you had this additional bit of information, you could work out where this electron was actually going to end up. Okay, and Heisenberg came up with a mathematical formulation which was on matrix mechanics, okay, that predicted the results accurately. So it could work out the probability. So there was a 3 in 5 chance of it appearing in C and a 1 in 5 chance of it appearing in A. Yeah, and that's as much as they could do. So it represents a retreat for science, quantum mechanics, in that we can no longer tell what's definitely going to happen. We can only predict the likelihood of anything. Okay, so this was a major thing, because everybody had this idea that science could tell you, given a fixed set of starting circumstances, exactly what's going to happen. It can't. It can only tell you the probability of something happening. Okay, and so Heisenberg came out with this matrix mechanics, which is very complicated, and not many people could really think about it. Plus, he was a Nazi, so people didn't really like that. he also came up with an experimental principle called the uncertainty principle.
What?
The Heisenberg uncertainty principle.
I never heard of that.
Okay, so the Heisenberg uncertainty principle says you can't know, there's a limit to what you can know about anything, because when you get really, really tiny, yeah, the things you use to measure, yeah, prevent you, in order to get, if you imagine a car driving past your window, okay, and you take a picture.
Yep.
Yeah. If you use a really fast shutter on your camera.
Yep.
Yeah. You click, and you see it, and it on the photo it just looks like it's stopped because the picture is so, you know, the shutter's so fast that it's just stopped. So, and you note down the time that you took the picture, so you can say, right, at this time, I knew that the car was exactly there. Yeah, so I knew a lot about its position. And somebody says, well, can you tell from the picture how fast it was going?
Right.
Yeah, and you say, well, no, because it just looks like it's a stopped car, because the shutter speed was so fast, you know, it just looks like a stopped car. So you say, right, well, I know next time the taxi drives past, because it's just going round and round and round, because, you know, it's just trying to scam somebody. So it's just driving round and round the block. So, right, when it comes round again, I'm going to use a slower shutter speed.
Right.
Yeah, and I'm going to open the shutter here, and then a second later I'm going to close the shutter. So you say, right, click when it comes round, and you see this blurred car on the photograph, yeah? And so you say, right, at this point, the picture starts, and a second later the car is here. So from that I can work out how far that, going from the end plate, the bumper to the bonnet, I can work out how fast the car was going over that period of time. Yeah? So on my second picture, I look at the picture and I can say, wow, I can work out exactly how fast he was going when he drove past my house because of my slow switch. And somebody comes along and says, yeah, but where was he? What was the exact position? Yeah? So in that example, you can't know the exact position at a point in time and also its speed. You can have either or, yeah? And the more you know about the speed of the car going past, yeah, so if you left the shutter open for even longer, you'd have more information about the speed of the car, but you'd have even less understanding about the position of the car. So as your knowledge of speed goes up, your knowledge of position goes down, and that is in essence the uncertainty principle. Yeah. So the more you know about a particle's position, the less you know about its momentum or its direction that it's going in and things like that. Yeah.
Yeah.
So, and that's the uncertainty principle. There is a limit on what you can know about a particle. And again, that was quite a departure from what people had thought. You know, you shoot a billiard ball across a table, you can work out incredibly accurately its position, its momentum. And there's another facet to the uncertainty principle, which is time and and he's fainted with confusion.
I fainted, yeah.
Yeah. So Heisenberg came out with all this great stuff. He was unfortunately a Nazi, so they didn't like that. And so Schrödinger, who really liked waves, he was like super into waves, and he really liked Broglie's matter waves. He came up with his own formulation, known as the Schrödinger equation. Yeah, that used things called wave functions. So for every particle, you know, you could work out a wave function, and the wave function is just the total amount of information that you can work out about a system or a particle. Yeah, that's all it is. It doesn't exist in real life. There's no such thing as a wave function in real life. Yeah, it's just the sum of all of this, all the knowledge you can know about a system. So it's limited by the uncertainty principle. Yeah, because you can't know everything about a particle. You can't know its position and its momentum beyond an arbitrary limit. and it's just the total amount of information that you can know, and then the wave functions that satisfy the Schrodinger equations are the ones that are allowed. So it's a good method of finding out, well, is this energy in an atom? Is this energy of a ball falling on Earth? Are they allowed configurations? You remember I said there were these steps?
Mm-hmm.
So to work out which steps were allowed in any atom or anything like that, you can use the Schrodinger equation, or you can use the matrix method. So Heisenberg's matrix method and Schrodinger's wave mechanics are equivalent. Yeah. Only in Schrodinger's wave mechanics do you get things like wave functions, wave function collapse, and all this wavy stuff. You don't get it in Heisenberg's matrix mechanics, but they both give you the same answers. So they're both sort of reverse engineered ways of telling you. So going back to the original 5 problems that we had, yeah,
Mm-hmm.
the atomic structure, yeah, Niels Bohr found out, and he came out with all of these different shapes of the electrons. So the electrons were bound, but they were acting like waves around the atom.
Mm-hmm.
Yeah, and that's why they were quantized. So if you imagine a guitar string,
Yeah.
yeah, when you pluck a guitar string, it goes wow. Yeah, but only certain notes are allowed.
Okay.
Aren't they? And as you shorten the guitar string by putting your finger on the fretboard, you get a higher note.
Yeah.
Yeah, and when you lengthen it, you get a lower note.
Mm-hmm.
Yeah, and what he said was, you know, the electrostatic attraction
Mm-hmm.
is in effect a shortening of those strings, so you get these different notes, if you like.
Mm-hmm. Yeah.
And those notes are integers, so it's a whole number of half wavelengths is the integers that you're allowed. So if you think about it like that, it's slightly different because you get different numbers. But if you think about it like that, it makes more sense. So the electrons that are closest to the nucleus,
Mm-hmm.
yeah, have, if you think, are high pitched. Yeah, and the ones that are further out are lower pitch, if you like. I mean, it's completely opposite to that. But if you think about it like that, yeah. And when you're adding energy in, you can change the energy of the electron, so it fights against that electrostatic repulsion, and it goes from the note A to the note B, let's say, yeah.
Yeah.
And then it goes wow and makes the noise, and then
You
finally,
sounded just like a guitar then.
wow, chicka, bow, bow. Right. So yeah. So but what you notice is the energy that's in the string is emitted as sound energy, isn't it?
It is.
Yeah. So it's knocking around the air molecules around the string and around the big part of the guitar, which I don't know the name of, and it's making a noise, and the energy is being transferred from the string into the environment. So it starts going quieter again and goes back to its original setting. So it's here, but in atoms it's this energy level goes down to that energy level.
Okay.
Yeah, it doesn't go wow. It goes wow, wow. And when it goes from here to here, it emits a photon of light. And that photon of light is related to the energy of that level, yeah? So like with notes on a string, we'd say it's either A or it's B. There's no wow or anything. Yeah?
Yeah.
And so what they did was work out from the Schrodinger equation the different combinations of notes or orbitals that these electrons were allowed to stay in. So you can put in anything into the Schrodinger equation, but only certain ones satisfy it. Yeah, and there's different, the quantum numbers are something, and if you think about those as being, if you like, equivalent to the notes. So you've got the principal quantum number, So in this is only in stationary obviously, principal quantum number, angular momentum quantum number, magnetic moment, and spin. And these are just numbers that are allowed. But the good point about it is you can check any proposed, you have an idea, I think this might be this wave function or whatever, and you can check whether it's allowed in that system. So again, it's trying to get back some of that science can tell you this information. Yeah. A guy called Dirac came along, another British genius came along, and made it relativistic as well. So he added relativity to the Schrödinger equation. You remember we were talking about relativity with Einstein? So to make sense and try and tie those things up a bit more together. And that's the sort of formulation of the quantum mechanics. What they noticed when you I'm just trying to think what to talk about. This is going to make any sense at all. There is something that happens to very small things, but I'll go back to that quickly. So they were saying, okay, you had these two formulations, the matrix model and the wave mechanics model, and they both gave the right answers. They both came out mathematically. But in terms of interpretation, in terms of what's actually going on, how do I picture this? It still isn't there. Yeah, there's no interpretation of what's going on.
Right.
Okay. So and what do people tend to do when there's no knowledge of or interpretations? They posit God, or
they say God did it.
They say God did it, or magical elves do it, or something like that. And that's kind of where it is now. And there's some other weird functions of what's going on, and that's something called entanglement. And basically, entanglement is when two particles or one particle becomes entangled with itself. So something you do over here to this particle affects that particle over here. And entanglement is really the source of all the weirdness in quantum mechanics. So when an electron goes through those double slits, it gets entangled with itself, and that's why it starts acting like a wave. You say it's a particle going through and it then starts acting like a wave. Well, I've gone blurred. Which is a good example, very imprecise about my position. But so it starts actually, it doesn't act like a wave, okay? It doesn't act like a particle. When these things are being really, really tiny, that when you hear people say wave-particle duality, or you hear people, it's acting like a wave, or it is a wave, or it is a particle, it's acting like a particle, it isn't, okay? They say these things because people understand what a wave is, and people understand what a particle is. Yeah, it's to get at the weirdness of how it actually is. What they did was, something called the Copenhagen interpretation, which is very mathematical. It's known as the shut up and calculate interpretation of the results. It was cobbled together at a time when they didn't really know what was going on because they were just discovering it. So they said, well, how can we teach people this? And you say, well, it's kind of like a wave in these circumstances, and it's kind of like a particle when it's in these circumstances. But it's just snippets of classical wave mechanics and classical mechanics cobbled together to give you the right answers when you calculate it in. It shouldn't be mistaken for wave functions exist, these things are real, until you can come up with an experiment that shows these things are real. As I say, the Heisenberg matrix mechanics gives the same answers as the Schrödinger equations, which uses things like wave functions. So you can answer these questions, you can formulate quantum mechanics without the need for these things which have got into the collective consciousness, and so you hear things about, conscious observers can, if you are what makes the universe real, and when you observe things, they start to exist, and when you don't observe things, they don't exist, and all this sort of thing. This is an interpretation of an interpretation that was invented in order to help people understand what was going on mathematically. But when still, and people will correct me because I deserve correcting. But you've got these. It's like whenever you explain anything to somebody, you have to give them examples of what it's like to them. Jimmy.
As I was just about to say, because you obviously heard how complicated this stuff is, but certain people that both Dazzletag and I know of take all of this to a little bit too far.
Yeah, so people will.
So you go from everything you heard, essentially saying that basically only the mind exists, as in when our conscious observation is what creates the universe. So these people essentially believe that if we've never seen the moon is just this, in the words of Deepak Chopra, a quantum soup of just like mathematical information that once we look at it will assemble itself.
Yeah,
and then become a moon.
And it's
basically it's sort of like a video game.
Exactly, and it was caused by, and this isn't to say it isn't true, okay? This is just to say that quantum mechanics does not tell you this. But the imprecise language that was used in order to teach people how it works and get people behind it so that they don't mind that their tax dollars and tax pounds go into researching it. You use quite imprecise language, so like the observer effect, okay? Now, the observer effect is where you, in order to find out, say, the initial conditions of a system, you measure it. Now, whenever you measure anything, if you think of a car tire, yeah, and you go, what's the pressure in your car tire? How do you measure that? Yeah, you get a little thing that you put over the valve, and you press it down, it goes, and it takes a reading. And it tells you what the pressure in the tire is. Now, it approximately tells you what the pressure is in the tire. The thing is, you've had to reduce the pressure in the tire in order to measure it. Yeah. So whenever you take a measurement, you do, to a certain degree, affect the system that you're trying to measure, because we're all, the thing you're measuring is probably made of atoms. The thing you're using to measure is made of atoms. So you've got this problem where these damn things are so sensitive and so tiny, and we haven't got anything that's smaller than them to measure it with. So you get this problem that's not the uncertainty problem, it's the measurement problem. And it's the same, you say, is there anything left in the fire extinguisher? I'll test it. Shh. Yes, there was when I pressed it. And you say,
how silly.
Sorry, how silly? Yeah, I mean, it is silly. But I mean, and I can tell, Danny, that this perhaps seems irrelevant to the majority of your day, and I can understand that.
Do you know what? I confess that I'm finding this interesting. I confess that there's very little I can say because I literally know nothing about this. And I'm going to have to fly because I got a call at 2 and I need to prepare.
Oh,
however, I will watch the rerun.
Exactly.
Take notes. You'll take some notes.
You'll take some notes.
We'll do a quiz next time.
We'll do a quiz next time.
Quiz me.
What, quiz you now? No, I wouldn't quiz on the basis
let me revise a bit first.
Yeah, I think if you, as with all these things, I always say don't take my word for it. Go look up these things, and hopefully this has given you some sort of awareness of what quantum mechanics talks about, the things it covers, the things it doesn't cover.
Do you know what it's actually done, amongst many things?
Confuse you and make you hate science.
No, it's made me think. It's made me think I want to go and invent a meter or a gauge for fire extinguishers.
I tell you what, Danny, this is what happened when Heisenberg came out and said there's an arbitrary limit. You can't know one thing to the other. All of the people that heard it and read about it said, "We'll see about that." And they all went out and invented all different types of apparatus and mechanisms to try and get over it. Nobody's done it yet, but if you can, you'd be a bazillionaire.
Well, nobody's managed. Has anybody ever tried to invent a gauge for a?
For a fire extinguisher, I imagine so. But the point is most when they test fire extinguishers, they tend to go.
And that's the madness, and that's what I'm thinking.
Exactly,
Imagine if you had that was the last drop, and as a subsequent result of, let's see if the fire extinguisher's got anything in it. What you end up doing is using the last bit, and your office burns down.
Exactly. I mean, say you've got a 6-shooter, but you can't see the bullets, so you just go, is there any bullets left in that gun? Yeah.
Yeah.
And that's the whole measurement problem.
And so I'm gonna think over that. I need to dash, gentlemen, because I've got to read through this proposal before I speak to these gentlemen.
Go into your business.
And do my business. I ought to try and earn some money to fund these 3 hours that we spend together learning topical stuff.
Yes. Well, I'll let you crack on.
Thank you, gentlemen. Cheers, Jimmy. Cheers, Dazzler.
Bye-bye.
Bye, Danny. Oh, there he goes.
Bye.
He's still there. Off you go, Danny. There we go. So, Jimmy, did you understand any of that? I felt like I prattled through it extremely quickly.
I'm proud to say it seems like I knew more than he did.
Yeah, hopefully you do. Cause
then again, that is because I've been learning this stuff more recently, and he hasn't probably been.
No, exactly. I mean,
probably hasn't been doing this type of stuff in over a decade.
Yeah, I mean, this is the thing that I think we come up against in a lot of people who see the videos on these debates that we have. I should just say we do spend a lot of time having debates about, does quantum mechanics mean free will? Does quantum mechanics mean that reality is false? Does quantum mechanics mean that if you wish for something hard enough, it appears? And of course, the answer to all those things is no. But there are people out there that use the lack of understanding or the sort of pop science understanding of stuff to then back up their own ideas and theories about the world. But from Danny's reaction, it's quite interesting. Danny's reaction, the kind of, why does this even matter? What's going on? Do you know what I mean?
And I mean, that's understandable, because I mean, a lot of complaints about physics is that a lot of people don't see real world applications for it. Unlike something like biology. For biology, there's a lot you can apply, but to a lot of people, physics is very theoretical.
Well, I mean, it's quantum mechanics that of course allowed the first transistor to be made, which is all computers and all that sort of thing. But of course, we tend to focus on the underlying minutiae of. I mean, in terms of quantum theory, that's kind of I didn't really talk about quantum electrodynamics or anything like that. But in the way that the Schrödinger equation allows you to say, well, is this configuration possible? Yes. What's the likelihood of the outcomes? Think if you consider that starting point, either in a stationary system or an evolving system. Quantum electrodynamics allows you to talk about how particles interact with one another and how light interacts with particles. And the Feynman diagrams are kind of similar in that they take the equations of quantum electrodynamics and put them into a picture format that will tell you, yes, this is allowed, no, that is not allowed. So for any, if somebody wanted to look into, does quantum mechanics allow free will, you would need a mechanism for free will first, which does not exist. And I know people go, oh, what about STAT 2005? Doesn't propose a mechanism. But you could then say, right, well, is that mechanism that's proposed allowed under the Feynman, in the Feynman diagram? Presumably there's some interaction between particles. Draw me the Feynman diagram. Is it possible? And once you can do that, test this idea.
This actually is relevant to one of the links I have here. It says fluid pet. This is actually it is on it's on simonsfoundation.org, and it was recently posted. The title is "Fluid Test Hint at Concrete Quantum Reality," and it's essentially I could link it, but basically some recent experiment gives evidence for more for determinism instead.
Yeah, so I think this one
pretty well.
is there was a interpretation of quantum mechanics. So, I mean, I should make that clear as well, if there is anybody watching this damn thing. There's there's the formulation of quantum mechanics, and there's the interpretation of quantum mechanics. And what tended to happen at the start was people came up with these interpretations in order to try and understand what was going on, and these interpretations persist to today. And what Feynman meant when Feynman said nobody understands quantum mechanics, he didn't mean nobody knows the maths of how to predict X, Y, and Z. What he said was there's no interpretation. Do you know what I mean? There's no useful interpretation that allows you to picture in your head exactly what's going on. You can only do it.
What was his name? Sam mentioned, that one study done by Chalmers where they asked a bunch of scientists, and there was not really any real interpretation that was, universally agreed upon at all.
Yeah. So, but the interpretations can be useful. So you can come up with an idea like this. The one that's being talked about in there is the where is it? I think it's the is it the Born interpretation or the Bohm?
I'm not familiar with that one.
Yeah, so the Bohm interpretation says wave functions are real, and what's it called? Wave functions are real, and they're a pilot wave. And so what's actually happening is the classical particle is coming through the classical hole and following the classical wave of the wave function. Slightly weird because the wave function is a complex part, so it has a complex part to it. So there's a part of it that isn't mathematically real. But yeah, and this pilot wave thing happens, and I think that's what this is talking about, isn't it?
I think so.
Yeah. So what they're saying is, I
could post it in the comments later.
Yeah. So wave functions are real in the sense of this pilot wave going through space. So that each particle has a separate wave attached to it. So de Broglie said, yeah, there's a wave associated with every particle, and that's why there's this idea of wave-particle duality. But I mean, people should realize that this is not a satisfactory explanation of, just saying, well, wave-particle duality, because sometimes it acts like, it's most easily understood when you apply a wave-like model to it, and other times it's most correctly understood when you apply a particle model to it. But of course, neither of those things really explains entanglement. What's happening? Why do you get the superposition of states? Why, what actually, of this mathematical formulation, what parts of it are real and what parts of it are useful but not real in order to get the right answer out the other side?
Now, is it even possible to know what is the correct interpretation, if there is a correct interpretation?
Well, I mean, I think with all science, you've got an interpretation of what's happening. So if you look at Newton's law of universal gravitation, and F equals ma, which you can link those two to link the sort of weight mass of something and its inertial mass, its resistance to changes in acceleration. Once you make the step and say those two things are the same thing, you can work out mathematically why things fall at a constant rate, a constant acceleration to the Earth. Yeah, everything falls at the same rate, but it doesn't tell you why things fall at all. What is gravity?
Therefore God.
Therefore God. So it doesn't tell you those things. So you kind of come up with an interpretation, and if that interpretation is good, it allows you to then say, well, if that's true, what are the other implications of it? And those implications might be useful in creating a new theory, a new idea that is testable. You know, so interpretations are incredibly useful. And just because the Schrödinger equation uses wave functions, which probably don't exist in reality, but if they're shown to be, then yeah, they are. But they were an invention in order to make the Schrödinger equation work that you don't need in the sort of matrix mechanics of Heisenberg. So, but if they are real, brilliant, you know. But there's nothing to say that they're real at the moment. But that's not to say they're not useful in order to think about it. But the problem is in the way people talk about these things. You know, where you know, Dirac's talking about this state, what's the probability of this state collapsing into that state? Yeah, you then get this thing in people's head of going, oh, the wave function collapses. And then people start going, well, that must be what happens in free will. You know, there's all of these different options, these superposition states, and we collapse it down into the one we want, which is just determinism. You know, it's saying there is no randomness. There is a hidden variable, and we control that hidden variable, and it then collapses it back down. But wave function collapse in reality, because it doesn't exist in reality, it's completely undefined. You know, nobody can tell you the time it collapses, or what the process of collapse is, or when it collapses, what it means when it collapses, and all that sort of thing, because it's a mathematical thing. It doesn't exist in reality. You know, you may as well just say it just happens. It's magic. Shazam.
But you know, that's not enough.
Exactly, it's not a satisfying explanation, and in fact isn't an explanation at all. You might think, you might say, or you might suspect that this is what's actually happening with free will. I don't get what they mean by this, because as I say, you don't need, if it's just going to be a deterministic approach, i.e. I can imagine 7 different outcomes, I'm going to choose this one. That's entirely deterministic. What you're doing is control, you know, if you can predict beforehand what you're going to choose, there's no randomness in there. There's no sort of, well, I'm going to fire this calcium ion out, and it's got a percentage of, discuss entanglement if you don't mind. So we'll select that one from Helena Handbasket. So we're selecting, so this is discuss entanglement if you don't mind. So entanglement, which is the sort of weird, the source of all weirdness in quantum mechanics, is each wave function. Say you've got the double slit experiment. I'm going to assume that people have heard of the Young's double slit experiment and what it means. And sometimes it acts like a wave, and sometimes it acts like a particle. But when you think about what's actually happening when I fire a single electron through these double slits, and I get something that suggests there's a wave pattern on the other side. I get something that suggests there's a wave interference pattern, which is suggestive of waves on the other side. What's actually happening? And it's as if the electron is interfering with itself. So if it is a wave, it's interfering with itself. Okay, so the idea would be the electron splits, goes through both holes, and as Feynman would say, it goes through all possible paths. So you know, the electron goes up around the moon and the Earth and all this sort of thing, and all these different separate paths. Excellent, thank you. All go down to produce this pattern on there, and there's probabilities that you can assign to each path. Yeah. Now, because they only go around each path once, it's as if they're communicating with each other, and that was the kind of the first. That's entanglement as it relates to the experiment there. so those properties that are that if you measure on any path, it affects the other path. Yeah, so if it went this way, it didn't go that way. Yeah, and there's all the different properties. So the spin of the electron. Let's just focus on the spin of electron. So if I measure the spin here, if I've got two particles, oh yeah, somebody's just gone, what? Yeah, this is not a good explanation. If I've got two particles here, okay, the total spin of that system is, let's say, 0, but this is like half up, that's half down. Yeah. Each of them can be either half up or half down. If I measure this one and it turns out to be up, that one's down. So the potential that that one's up is now 0. The probability that's up is now 0. The probability that it's down is there. Now, if you move these two things apart, and apparently even in time as well, yeah, so if you set this one up in a space rocket and flew it around at the speed of light, so there was a timing difference as well. When you measure it, it appears that the outcome of this one affects the outcome of that one. An entanglement is this where you have a system, a quantum system, so a wave function that's calculatable, where the measurements on one affect the measurements on the other. And this was a big problem to Einstein. I mean, it wasn't really a big problem for Einstein. He came up with this problem saying, if this were true, then there's non-local properties, and that was confirmed through the what was it called? Bell's inequalities. You know, that there were no hidden variables, that you could not say that this one definitely, you're not just finding out, you're just doing that. So the problem was that this was happening at all, because you would imagine that things are discrete. So you've got an electron over here, and if it's not linked, if it's not next to the particle over here, how can something you do here affect something over here? This is a really bad explanation of entanglement. But it's a product of the maths of Schrodinger's equation, and it seems to happen in reality. I'm just umming, just loads. So, and it's a product of the fact that if you've got a wave function for any system, you've got a number of different possibilities of outcomes. You've got a series of allowable outcomes. And what happens when you do the experiment is that when you measure a particular state here, it's not open for this one to have the same state. They've got to be different. People have said it's like if you imagine rolling a dice, and if you've got two dice, a black one and a white one, they could both, and you hide them in both hands. In this one, it's white, therefore that one must be black. Yeah, but the thing with superposition states, they don't settle into one state. They don't collapse into one state until you actually measure it, until you actually observe it in the sense of taking off the quantum state through a measurement. Then it fixes the other one. Now, if these are that far apart, yeah, Einstein would say, well, it's got to be, you can't transmit information faster than the speed of light. But when you look at, you look at this state over here, you see that there isn't actually a transmission of information, or there probably isn't. But one, this is weird because you would imagine that doesn't happen. And nobody's really come up with a good explanation for entanglement. It's one of these things that just happens.
And it brings up Schrodinger's cat, where the cat is both apparently dead and well, it wasn't really the whole point of that. The whole point of that experiment was saying that.
No, I mean,
saying how you can't bring that to the macro world.
Yeah, the problem with and I apologise for that terrible discussion of entanglement. I mean, at the moment, I think the most they've entangled is about 30 particles. Okay, and this is part of the reason why you don't see quantum behaviors at the macro level. You know, a person is probably not one entangled system. A person is a cluster of, you know, atoms and individual atoms and things like that. To see the wave pattern on behind the double slit, okay, you need to have an entangled system going through it. I mean, I think they've done it with like a buckyball. And so these things have to be, in order to get the interference pattern, the wave element of it in wave mechanics must be in phase. So they've got to be entangled when they go through. You've got to have entangled. That doesn't happen with a person because they're so, you know, they're so large and complex that the path differences that you get with diffraction just don't happen because they're not all in phase with one another, because they're not entangled, because big systems don't stay entangled for very long. So this is just, you know, the reason it only affects tiny little things is because you can keep those things entangled. Things that stop entanglement are things like the observer effect. Yeah. So if you imagine a molecule of whatever sat there, or something big sitting there, and you get an electron or something coming down, or a photon coming down, and it pulls the electron off and draws the thing down, it's going to affect the quantum system. Do we know?
Are you reading the comments?
Yeah, sorry, yeah, I will. I just finished this. So the point is with the entanglement is that very large objects would decohere very, very quickly, or, you know, quantum information would be changed by interaction with the environment to the point where it doesn't act like an entangled system. So Schrodinger's cat, it just dies in the box. Yeah, it either dies or it doesn't. The cat is just as good an observer, or the Geiger counter inside the thing is just as good an observer as somebody realizing that the cat's dead. I understand that there's this idealism thing where if a cat dies in the forest, it isn't dead until somebody finds it. You know, which is just a zoomed up version of the cat in a box, you know.
But,
so
you know, they fail to realize that, you know, Schrodinger's, you know, that experiment wasn't, I mean, it was serious, but the whole point of it was to say, look, you can't take this and then expect, you know, bring it to the macro world. I mean, it's absurd to believe that the cat is both alive and dead at the same time.
Yeah, I mean, if you look at how hard it actually is to get light to diffract, and I know people say, oh, you just put it through a diffraction grating. Yeah, but it's got to be monochromatic light. It's got to be exactly the same frequency and exactly the same wavelength to actually get these things happening. Light is all around you. There's radio waves all around. There's microwaves all around you, and all that sort of thing. They don't interfere with one another. You know, you don't start diffracting when you walk through a door. If you do, it's in such a tiny amount that it's undetectable. So these things are only pronounced because they're small systems. Anyway, that's entanglement. But go look it up. I mean, I apologise profusely for my rambling nonsense. And so
I might as well bring up the other link I have here, where, well, it says that, of course, this is pop science, so of course, you know, they're journalists, but it says quantum effects spotted in a visible object.
Yeah.
And physicists in California have observed true quantum behavior in a macroscopic object big enough to be seen with the naked eye. This is the first time this feat has been achieved and could shed light on the mysterious boundaries between the classical and quantum worlds.
Right. Which is great. It just means that these things aren't decohering. Do you know what I mean? They would have obviously, I imagine, I've not seen this, but I would imagine it requires a few feats of separating it from the environment.
Yeah. I posted it here.
Let's have a look. Physics World.
Yes, the same website you sent me that other thing.
Okay. Micrograph of the resonator. Oh, there you go, buckyball. Yeah, so the challenge here, in order
so you were talking about it. Okay.
Yeah, so scientists have long wanted to demonstrate superposition in larger objects, but a significant challenge here is to eliminate all thermal vibrations in the object, which mask or destroy the quantum effects. Yeah, so because heat is just the wobbling of stuff, yeah, the problem that you have is you lose things going out of phase, so that you don't see these things. But what they've managed to do here is cool down to its quantum ground state. So once you can get down to like absolute zero, the vibration, you'll never stop something vibrating completely, because otherwise you'd know the energy and its position, which you can't do under the Heisenberg uncertainty principle. But you cool it down enough and look through a magnifying glass, and apparently you can see this, which is great. But the point is, of course, that you have to isolate it from all of the things which will cause these things not to be entangled. Things that remove entanglement.
And you know, like you said, the word vibration is used a lot in the certain quantum woo circles. Not specifically like, idealism, but like more of the Deepak Chopra. They love everything is a vibration, which is true, I guess, in a way. But they mean that to mean in another way. They say, okay, so you're sick because you're not at the correct vibrational frequency.
Oh, yeah,
so you
exactly.
need to get in tune.
Yeah, and obviously there's nothing you can do mentally in order to prevent interference from the environment around you. You know, short of sitting in a vacuum at absolute zero, you can't control these vibrations or anything like that.
I don't know if the vibrations are good or not. I don't know enough about quantum to figure that out.
Yeah, but yeah, so if your heart center is open and your groin chakra is correctly aligned, then you can control entanglement. The point, I mean, one of the points is about this, this whole realism and things like that, is the more you look at something and the more you remove interactions with the environment, the more you realize that objects tend to be just processes. Yeah?
What do you mean by that?
So you have these things like entanglement. Well, if I mean, be careful. I'm not saying that these things don't exist. I'm not saying they're not real. It's just their existence depends on things external to them. Yeah, because it's a product of their interaction with things. Magnetic force, if you like. Yeah, do you know what I mean? It's a process, not an object. And actually, the more you look at things, the less they seem to be. To have their independent, totally independent of anything else, any other field or any other thing like that. It's just it's a process rather than a discrete object. What you perceive as like a photon is three quarks interacting with one another. So you say, well, what's a quark? And then you probably find out that quarks are made of something else. In any case, how do we know that there might be some? So I'll ask the next question. Do we know that it's not that there might be some hidden variable mucking it up that we just don't know about yet? Have we excluded that possibility completely? Yes, we have, or at least yes, we think we have. Again, all of these things are entirely open to new knowledge and new information. What was his first name? Bell. He was an Irishman. Anyway, he came up with the idea of Bell's inequalities, and it was in response to Einstein's EPR objection. So it said, well, because Einstein said, well, you've got this spooky action at a distance. That's weird, because most of all other physics is you don't have this. You have action, photon, action over here. You don't have this sudden move here and the other thing moves at the same time. There's it's not instantaneous. It's so his famous one about gravity. It's the shape of space-time. It's not some magical power between the two, if you like. I desperately want to find his first name. But it does it. But anyway, so Einstein came out and said, you know, it's either local or it's counterfactual. Counterfactual and local and quantum. It can't be all three. So this whole thing of entanglement, where you measure one and it affects the outcome over here, this spooky action at a different distance. So what he said was, if maybe there's some thing that we're not seeing. So he came up with this idea and experiment. And so Bell came along and said, right, well, if it's this and this, if it's this and this, or if it's this and this, then there's this problem. And somebody came along and said, yeah, I'll do that experiment. They did the experiment, and they proved that there are non-local, that certain properties are not localized. So the properties of the system are additional to the properties of the individual things, or there's certain properties of a particle which aren't localized. Yeah, I mean, it's hard to come up. It's hard to think of an example. But I mean, if you think of spin, which is this thing that it isn't really spinning, but you just call it spin. Okay, the spin property of the particle isn't localized until you localize it. So until you measure it on this one, and you say, oh, that's spin up, then this one becomes spin down. So what they established is that there are non-local, there's non-localism, and there's no hidden variable, there's no mechanics inside the electron that's causing this to happen. There were some other experiments that said, are there any non-local hidden variables? So there's Bell's inequalities show that there are, inequality paper shows that there are no local hidden variables. There was then some other experiments, and I apologize because I can't remember that, that showed there are no non-local hidden variables. So because if there were, then quantum mechanics wouldn't be true, and it's as annoying as that. So yeah, there are no hidden variables in the particle, and there are no non-local hidden variables in the particle. So these ideas about free will and being able to control the outcome of an individual particle. So you fire a particle, where does it end up? You know, we can still only predict the probability of it ending up in specific locations. We can't say where this individual one will go when it flies through. So there's nothing in the mechanics of the electron as it goes through the slits. There's no wheels or cogs inside it that goes through. It's related only to the initial state, and there's no non-local. There's no non-local influence that's making it only appear to be random. Okay. Now there are interpretations of quantum mechanics. So I'll click on done. There are interpretations of quantum mechanics that do try to explain the randomness, and that's like the many worlds interpretation, where the superpositions each individual superposition creates a new world, a new universe. So if there's a, you know, does it, you know, when I measure it, is this one up, is this one down? You know, in universe A, yeah, in this one, it's this definite outcome. In universe B, it's that outcome. So, and you just happen to be in the universe that, you know, is a combination of all these different ups and downs. And things like that. And that's an interpretation that might yield some answers and might give some super fun big time. Jimmy. You still there, Jimmy? I've got a horrible feeling he's making his damn breakfast.
Sorry, I'm here. I just need to. I need to mute my mic for a second. I'm listening.
Yeah. So that is what else do you want to talk about? No. Why have you muted your microphone? This is now just me sat talking to myself. Let's have a look. Sorry, you've got nothing. Okay, let's just have a quick look at the non-local hidden variables and just this is so boring for people. EPR paradox does. John Bell. He said that if local variables exist, certain experiments could be performed involving quantum entanglement where the result would satisfy a Benn inequality if, on the other hand, statistical correlations resulting from quantum entanglement could not be explained by local hidden variables, the Bell equality would be violated. Another no-go theorem. Kolbeck and Renner published a proof that any extension of quantum mechanical theory, whether using hidden variables or otherwise, cannot provide a more accurate prediction of the outcomes, assuming that observers can freely choose the measurement settings. Oh, that's an annoying phrase. In the present work, we have excluded the possibility that any extension of quantum theory, not necessarily in the form of local hidden variables, can help predict the outcomes of any measurement on any quantum state. In this sense, we show the following. Under the assumption that measurement settings can be chosen freely, quantum theory really is complete. So, I mean, which one? Which interpretation? The many worlds? I like the many worlds. So the question, what do I think about that interpretation? There are lots of different interpretations of quantum mechanics, some more probable or nice than the other. I do like the many worlds interpretation. There are lots of different interpretations, and people are free to like what they want. There's no right one. There's no wrong one. There's ones that are highly unlikely to be true. One thing with all interpretations at the moment, they all must at least produce the same answers mathematically as the Schrödinger-Heisenberg formulations. So they must all produce those answers. And one of the problems with a lot of these interpretations, or one of the criticisms with a lot of these interpretations, specifically things like the ones that try and drag it back to classical mechanics, so the Bohm pilot wave thing, is it posits something additional. It posits something additional that isn't needed in order to give the answers that you want. So, and Occam's razor would say, well, don't multiply these things and these assumptions unnecessarily. So don't, if it gives the answer without the pilot wave, take the pilot wave out. But as I say, that's with these things, you always need to have people putting their neck on the line, their head above the parapet, or whatever, their arse on the line, in order to come up with some new ideas that somebody else might then go, oh, that's a brilliant idea. Why don't we then do that? I prefer the many worlds because it does answer the question. It's the only one I can see that answers the question of what is it that the electron going through the hole is interfering with. Yeah, so when you talk about things interfering with themselves, you kind of think, well, what do we mean? What do we mean by that? To a certain extent, how do you picture that? And where these things are interacting with each other in, the other world, if you like. And I don't mean that in the haunted, magical mouse world. I mean it in the sense of, between two universes, it's interfering with itself. You are doing the same experiment in both in the universe. It then splits when it's detected. So there's no randomness there. You are merely in the universe where that outcome occurred. And then those.
And what's interesting about it is, how it kind of, I guess, leaves open the idea of parallel universes. Like, is there a universe where you're doing this hangout, but you're just wearing green pants or something?
Yeah, so the many worlds interpretation says that everything that can happen does happen. So everything that can happen that isn't forbidden by the laws of physics can happen. So and you know happens. So say you take your best episode of Star Trek. As long as there's nothing in that episode that contradicts a law of nature, it'll happen. Yeah, so all fictions which are at least possible in terms of physics occur. So as long as it doesn't contravene conservation of energy, conservation of angular momentum, conservation of spin, conservation of charge, as long as those things aren't violated, then you can assume it
But almost anything else can. Like, couldn't certain things about biology possibly be violated? Like, instead of carbon-based life, it could be methane-based life, or something like that.
Yeah, I mean that can happen in this universe. I mean, there's no law of physics that prevents things being silicon-based, I suppose. I mean, the only problem with silicon.
There's a universe where you're Batman.
Yeah, if there's a universe where I'm really, really rich and and a genius, then yeah, I suppose I could become Batman. But as long as there's no physical law being broken, as I say, then why not? Because all of the, reality is just a stream of these, quantum mechanics. Although I say quantum mechanics you don't see these weird entanglement phenomena, which are the things people mean when they say quantum mechanical behavior. The entanglement phenomena. All of physics is quantum mechanical. There is no classical physics. At its lowest level, it's all quantum mechanical. Yeah. So all decisions, wherever there's a quantum mechanical interference or entanglement phenomena happening at the base of it, those in the many worlds idea that creates two universes. So say you've got a radioactive material that decays it ejects one alpha particle an hour on average, and you put that that lump of radioactive material into a box with a cat. After an hour, you open the box. In one universe, the cat's dead. In another universe, the cat's alive.
So in that sense,
but in no universe. Sorry?
Oh, never mind. Go ahead.
No, go on.
Well, I was just saying that, in that case, if many worlds was true, then yes, the cat is both dead and alive at the same time, but just in different universes.
Yes.
Is that what you're basically saying?
It's not alive and dead in any one universe, which seems to sort of align with what you would imagine to happen. There's a universe where as soon as you get any exchange of quantum, any change in the quantum state, you create another universe.
So wouldn't this mean that essentially, if it's true that there's basically I don't know how to explain it, but I don't know the word, but for every single universe, there have been one original one, and then from that point, every time it's split, it's like branches.
Yeah.
So
when
the cat is in the box, two whole universes or like a separate universe is made. One where it's dead, one where it's alive. And actually, there'll probably still be more variables. Where was the cat in the box? Was it on
Yeah. So if you imagine the owner of the cat comes in and says to her husband, Erwin Schrödinger, we'll call him, says, "What are you doing? Where's Mr. Snuggles?" And why do you possibly like? How can you possibly like the many worlds? Explain yourself. I suppose the reason I like the many worlds interpretation is it's the most sci-fi of a lot. I love it. Yeah.
Yeah.
So the wife comes in. Mrs. Schrodinger comes in and says, "Owen, what the hell are you doing? Where's Mr. Snuggles?" And he says, "The cat is in the box, and I've got this cyanide and this particle." And so she says, "Oh, get Mr. Snuggles out of the box." Now he opens the box and he sees that the cat is either dead or alive. Now in universe A, the cat is alive. In universe B, the cat is dead. In universe A, Mrs. Schrodinger forgives Erwin and says, "Oh, you, come on, Mr. Snuggles, everything's fine." In universe B, Mr. Snuggles is dead. And so they get divorced and they don't have children. And, so you've got these universes then diverging with events propagating out at the speed of light from there. And that's what I mean. It's really, really sci-fi. And like that and film, Sliding Doors.
I mean, we've always, it's, in fiction, we love, alternate universes, because, there could be an alternate universe where Hitler won and the whole world is controlled by Nazis.
Yeah, exactly. Yeah. But you couldn't have a world where you dropped a bomb, and it gave a different explosion. If the mass was the same, the amount of
it wouldn't explode, and there wouldn't be it wouldn't explode like rainbow fruit goodness or something. It would just
exactly
it would still be.
Yeah. And that is what the many worlds interpretation says happens. So I as I say, I love the extra worlds talk about adding stuff. Yeah.
There are some problems though, because I guess even if that, there'd still be some things that'd be more likely than other, like some alternate universes that are more likely than others. Like it's more likely that there's a universe just like ours, except for one detail, and that would be I'm wearing pants instead of jeans. But it would be a lot less likely that there's a whole universe where cavemen somehow invented nuclear fusion. So is it possible that that could happen? Because yes, I don't. The laws of physics wouldn't be broken, but how would it'd just be so unlikely that that could happen.
Well, I mean,
given the resource.
You then come up against what's infinity. So let's the universes will separate in the proportion of the so if you've got the slit experiment and you've got the central maxima, which is where most photons end up, and let's say N4 gets half of the photons, then there's twice as many universes in which it ends up in the maxima as it does on N4. Yeah, but there isn't an infinite number of variables in that. But yeah, you say, I mean, when you say it's unlikely to happen,
mean that if time,
you just need to. I mean, you've got to think of what's happened prior to that. If somebody comes up with a rule that you're only allowed to wear green jeans, then suddenly it's not incredibly unlikely that everyone's wearing green jeans. Do you know what I mean? The idea of random is, if you posit something and say, well, how do we get from where we are now to a universe where everyone happens to wear green jeans, then you can say, well, that's so unlikely to happen that everyone chooses to wear green jeans. But it doesn't have to be chooses. It doesn't have to be, this is one problem with randomness and what people talk about, especially not related to this, but when you talk about like the fine-tuning problem, and you say, oh, it's so random, it's like too random, so therefore God did it. And it's just like, well, you can have a process that makes it far more likely that what you're calling completely too random to occurs, yeah? Do you know what I mean? Like I say, somebody comes in, makes a law that says we're only allowed to wear green.
Yeah.
Diocletian.
That's possible.
Yeah, I mean, you could,
but possible.
Yeah, you could have a Jesus-like figure that says Christians wear green. That's what you have to wear, and if you don't wear, religions specify burqas or say specify whatever, and you say, yeah, you have to wear green, and let's say then the Nazis win, and so the Nazis say, well, we're Christians, so everyone has to wear green. It doesn't have to be as, people jump to this, oh my god, it's so stupid, totally random, that it's too random. So there's things that could happen that make it seem unlikely, but it's not necessarily unlikely. So the randomness that we're talking about is the outcome of those, the rules of quantum mechanics say these are the probabilities of certain outcomes occurring, and they're not necessarily infinite.
And of a lot of the whole reason you existed because your parents. I mean, I don't know how your parents met, but there's a chance that they could have never met. The odds are they never would have.
Yeah.
So
exactly. So if you say, do you watch Doctor Who?
I don't actually. I really should, but I don't.
Yeah. So in Doctor Who, there's a scene in Doctor Who where she's got her parents. There's a leaf that blows off a tree and covers one of her parents' faces, and the other one saves the other parent's life, and that's how they meet. Because a car's going to run her over or something because of this damn leaf. Yeah. So they say, oh my God, isn't that really? That's totally super amazing. Because if the tree hadn't grown there, and if the leaf hadn't fallen off at just that moment, and if the wind hadn't been right at just that moment, and if all of these different things, which seem really, 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 really unlikely, if all of those things hadn't, then you wouldn't be born. Therefore, the fact you were born is so amazingly unlikely that it can't possibly be a product of mere chance. It mustn't it be divine intervention? And of course it's nonsense because leaves fall off of trees. People can get hit in the face on it. It's not actually that unlikely, but you don't say, well, your mum and your dad are 2 in 7 billion. What's the chances of those two bumping into each other, mating and having a child? Isn't that totally amazing? It's so rare and random that it must be too rare and random. Therefore, God. And it's the same thing with the fine-tuning.
And of course, it's really easy to believe that. I mean, I've had similar experiences myself. I mean, I look at how I like this person, and it's just the odds of me seeing this person is just so low that you feel like it had to mean something, and that's natural for all of us, of course.
I absolutely understand where it comes from. When people, I imagine lottery winners feel that there's divine intervention. I can understand why George Bush believed in God. A man with no discernible qualities at all becomes the most powerful man on earth. Do you know what I mean? You can understand why
he graduated from Harvard.
Sorry?
He did graduate from Harvard, so I mean, it's hard to believe.
Yeah, therefore God.
Believe that, but he did.
Is probably what he thought. The point is, I may be polemicizing slightly when I say that about George Bush, but you can understand people who have tremendous fortune and who have tremendous power start to believe that there must be something in it. Just as you believe when you walk around the corner and bump into your crush. Or it was meant to be. And if you look at it in a certain way, it seems ridiculously random. But if you actually understand there's a process behind it, I mean, it's like, oh, how can you say that, the sperm that made me, that was one of 100 million. Are you saying it's not divine providence? It's just a way of backfitting.
Your lottery example was perfect. I mean, yes, the odds of you winning, of this certain thing happening is, of course, extremely low. But what is completely positive is something is going to happen. Somebody is going to win.
Yeah, exactly. Yeah, and it's just this belief in your head that there is a link that makes you think. I mean, go on.
Well,
Yeah,
you may meet the perfect person, and they are perfect, but for you, but is there really any, can you really say that they're the only person in the whole world that is? Like, was it really a 1 in 7 billion chance?
yeah, exactly. No, because you both lived in the same street, so it's very unlikely that you weren't going to meet. Do you know what I mean? It's like you have to look at it in the other way. I mean, when you say, you've heard this jumbo jet analogy. A whirlwind flies through a junkyard, and so will a jumbo jet, and that's why evolution is so unlikely to be true. Because what they're doing is saying, so it's completely random chance that all of the atoms come together in this one thing. It's absolutely ridiculous. Yeah, because atoms, this step from atoms to jumbo jet, they don't just go from here to here in one step. There's a whole process and a whole environment that's affecting that process, including people and engines and stuff like that, that then create this thing. But if you say, well, that's super unlikely that atoms would turn into a jumbo jet, yeah, it is super unlikely if you think about it in that way. But if you say, it's like any probability, you just measure the damn things. If you look at things and you ignore process, the things that select along the line, like natural selection takes a random variation, and that variation is selected, locked down, and then other random factors act on it until something that gives you an advantage comes along, lock it down, and selects those things. But if you look back and you say, oh my God, look at how random everything is. The Earth started and then my parents met. How completely unlikely is that happening? So therefore magic.
This would be a good idea for another hangout if we want to do something on evolution, but this also reminds me of the whole irreducible complexity argument.
Yeah, because you just say atoms eyeball. How can that happen? Pardon me. So yeah, so you have all that that happening, and as I say, it's always down to thinking about things in the wrong way, or being too credulous, to be honest.
We are, we're pattern recognition animals. We are, it was a evolutionary adaptation to find patterns, and this is, it's a good thing for survival because, let's say, if I was, a Stone Age person walking in a forest, and I hear I see a dark figure, and I see and hear a sound to the left of me in the bush, I'm going to, react.
Yeah.
And I'm going to, expect it to be something dangerous.
Yeah, because the risk is if you're wrong, no harm done. If you're right and you don't get out of there, harm done.
Yeah, and you turn left, and then you look at it and you say, oh, it's just a bunny rabbit. I was wrong, but yeah, like you said, it was worth the fear because what if it was a wolf?
Yeah, exactly. Yeah, and it's just that reaction. It doesn't happen in your brain, unless you count the spinal column as your brain. But yeah, and that's an adaptation. It's a product of evolution because all the people who didn't have that adaptation died and got ate by the wolf. Yeah. And so that's why that thing is so common amongst the thing. But you've got you've seen in what you're saying about the many worlds interpretation, you've seen how easy that is to fall into that particular trap, to say something is simply too random to happen. Well, it doesn't need to be random, does it? It just you just need an explanation. And each individual step is not unlikely. It's not unlikely that two English people will meet each other if they live in the same city. It's not unlikely that after they meet each other they want to hang around each other more. And it's not unlikely that they have sex. It's not unlikely that sex leads to children. And then you start getting into this what's it called argument where you go, well, if you weren't born, you wouldn't be here and marveling at the fact you were. Anthropic principle, you know.
Yeah.
When you say I'm one of 10 million sperms or whatever it is, you know, isn't it just amazing? Well, not really, if you remember, you know, because
you would have been somebody else.
Yeah, or you wouldn't have existed, and you would have, you know, their child would have been somebody else. But the fact you won a 1 in 1, I mean, I don't know how many sperms the average load expresses, but I mean, but the point is you go like, oh my god, I won the lottery.
I believe.
I won a 1 in 200 million lottery. Isn't that amazing? And you know, and the drive in your brain is always to think that. Is always to think, oh my god, this is like super awesomely amazing. Aren't I lucky? Doesn't Jesus love me? You know, because the other explanation isn't all that satisfying. You know, well, if you hadn't been born, you wouldn't be here marveling at the fact you were. It would be somebody else marveling at the fact you were. And this is the.
I mean, it's perfectly fine to marvel at it. I mean, in ways, but you shouldn't go from that to say, therefore, it was meant to be. You should be more humble by it. You should be like, okay, I basically was in a way. I shouldn't say I'm using this metaphorically, but you were gifted, in a sense, by the universe to have, you know, this
privilege of existence.
You know, this chance to be able to experience the universe.
Yeah, and I mean, it comes down to, you know, very large statistics, very large statistical models and statistical understanding being applied to one individual. So you look at smoking, say, and you say, right, 50% of all smokers die from smoke. 100% of all smokers actually die, but 50% die from some complication brought about from the fact that they smoke. Yeah. Now, for the individual, they're either going to die from smoking or they're going to die from something else. So this idea of 50%, for example, you know, it's very accurate when you look at a large population, but it stops being accurate when you get down to the individual. Because if you say to the individual, you know, there's a 1 in 14 million chance that you're going to win the lottery, you know, and they might think, oh, well, if I play the lottery for 14 million weeks, statistically, I should win once, you know, and they could win it in the first week, or they could never win it if they did 14 million weeks. You know, it's no guide to what's actually going to happen. You know, when you deal with lower probabilities like the 50% thing, it's like flipping a coin. Flip a coin once, and it's heads. Flip it again, it's heads. Flip it again. You know, if you flip it 1,000 times and it's all heads, you need to start questioning whether or not you were right about this thing, that it's a 50-50%, a 50-50 chance, because there's obviously something wrong with the coin.
You know, Carl Sagan kind of, you know, there's this whole pale blue dot thing, but, you know, like you said, when you look at it from an individual sense, you know, it's very, of course, it's unlikely, but you have to look at the bigger picture, and the bigger picture is somebody's going to win, or somebody's going to get whatever, or something's going to happen. It matters, you know, who it is or where it is.
Yeah, I mean, if you look at, say you get a lucky dip in the lottery, do you have lucky dips in America? Where you just say,
I have absolutely no idea what you're talking about.
In the lottery, yeah, you can either pick your numbers, yeah, or you can say to the computer, give me just pick any just pick numbers randomly. Okay. In the lottery in Britain, okay, you can mark off your own numbers. You can choose the 6 numbers that you want, or you can say, give me a lucky dip, and the computer just spews out 6 random numbers. Okay. Now, if you think about things in a statistical way, what you might think is, what is that person doing? That person is correctly guessing, or is through one action of saying, give me a lucky dip, is arranging 2 random systems, the computerized random system and the physical ball random system, to coincide on the same 6 numbers. You would say, that's impossible. That's so random, it's impossible. But it happens. This is do you know what I mean? People win the lottery with lucky dips. So what you need to do is then, you don't say reality is wrong. because it has happened. You say, right, your analysis of when you say it's so random it's impossible is wrong, because in reality it doesn't happen. Oh, in reality it does happen. Sorry, it's only you saying it doesn't. So when no doubt very clever people say that the constants of the universe are so random that they're too random, and so could not possibly have happened, except with Jesus, but could not possibly have happened. It's happened. You live in the universe. It is real. The physical constants do exist. Therefore, it's not as impossible as you say it is. Evidently. Do you know what I mean?
So, and I guess, how do I say it? It's us being very egotistic the way we view the universe. Like, I mean, there could be another Earth where instead it's. Is there any feedback? Like, is there like?
No, I'm fine.
Does it sound like I'm saying this any farther from? Okay. Yeah. But like, in another world or on the same planet, there could be. It could instead have a higher oxygen count, and there's like, an insectoid version of William Lane Craig debating an atheist.
So like here.
Over yes.
Yeah.
And they could be like, oh, look how unlikely this is that our planet has just this high amount of oxygen for our species of whatever insect we are to, grow this large. Otherwise, we would be, really small.
Yeah, well, what you
wouldn't be able to,
Yeah, what you should say is look at the entire volume of the universe, and then look at the proportion of that universe that is conducive to life, and for what a tiny portion of the universe's existence is that small area conducive to life. Do you know what I mean? If you looked at, 99.9999999% of the universe will kill you instantly. So if you were doing it in the sense of lottery winnings, you could say, yeah, well, life's got to happen somewhere, hasn't it? The universe is a big place. It's not that amazing. Even if it is vanishingly small, it need only be non-zero to occur, But the thing is, what they do is.
And I guess. Well, yeah, it's just you've heard of the Drake equation, right?
Yeah.
Yeah,
but Yeah, and it's looking more and more.
It's almost absolutely certain that there is intelligent life out in the universe. Now, we probably couldn't be able to understand it the way, like, it wouldn't be like gray, like little gray men, but it would be some type of life that we, that would have around our type of, reasoning skills.
You would hope, yeah. Well, you would like to think. I mean, the thing is, it doesn't require an answer, does it? You can look. You don't need to say it does or it doesn't. You can. I mean, what we tend to do is say, well, we kind of understand life as we understand it. Let's look for the things, the factors that allow life on Earth, don't you? So we say, let's look for liquid water. Let's look for oxygen in the atmosphere. Let's look for this, that, and the other. And it could be on Mars. It's one of those things. Like I say, the jury is out. But I mean, it'd be quite weird if it weren't, because the thing is that the people who say, oh, well, no, life only exists on Earth because Jesus, one day will look extremely foolish.
I mean, they should look foolish already by now, because the amount of research that's been done in Mars. I mean, it's a fact. Well, I don't know if I go far as to say it's a fact, but there's a huge amount of evidence to say that, like 3 billion years ago, Mars had oceans on it.
Yeah.
It was, habitable. Now, whether there was actual life there is, another question, but it's basically well known now that Mars could have had life. It had the very basic foundations for it.
Yeah, exactly. So, and you then sort of say, well, is it, should there have been life in there? What's the variables for life? And things like that. But with good scientific theories, universal scientific theories like evolution, like general relativity, and like quantum mechanics and stuff, they should be true no matter where you are in the universe. if there is complex life on another planet, it's become complex life through evolution by natural selection. Do you know what I mean? And that's quite amazing.
Yes. Well, I think we've gone enough off topic.
Yeah, we probably have. It's 3 o'clock now anyway, so we wanted to do this.
We went from 7:40 to 10 for me.
Okay, yeah. So it's almost your bedtime, Jimmy.
Yes, totally.
Yeah. So we'll leave it there. I'm sure I'm gonna want to delete this video because it was so rambly at the start. But no one's gonna hear this because I doubt there's nobody. I doubt there's anybody.
Oh no, don't. I think it was fine.
Yeah. I think the thing is with
it was fine. Yeah.
Yeah. Right. Anyway, so that's that then. So maybe see you another time. Bye.